Hi, here's something I find interesting, and I hope you will too. Our universe may contain 100 billion galaxies, each with billions of stars, great clouds of gas and dust, and perhaps scads of planets and moons, and other little bits of cosmic flotsam. The stars produce an abundance of energy, from radio waves to X-rays, which streak across the universe at the speed of light. Yet, as Shakespeare said, here's the rub. We only know and understand 4% of the total mass and energy in the universe. Yes, that's just 4%. These are atoms, stuff we know, or baryonic matter. As you can see in the top diagram, about 1/4 of the universe consists of dark matter, which releases no detectable energy, but which exerts gravitational pull on all visible matter in the universe. Whilst dark matter and dark energy may be related, their effects are quite different. Briefly, dark matter attracts, dark energy repels. While dark matter pulls matter inwards, dark energy pushes it outward. Also, while dark energy shows itself only on large cosmic scale, dark matter exerts its influence on individual galaxies as well as the universe at large. Astronomers discovered dark matter while studying the outer regions of our galaxy, the Milky Way. The Milky Way is shaped like a disk that is about 100,000 light years across. The stars in this disk all orbit the centre of the galaxy. The laws of gravity, according to Newton, say that the stars that are closest to the centre of the galaxy, which is also the centre of mass, should move faster than those on the galaxy's edge. Yet, when astronomers measured stars across the galaxy, they found that they all orbit the centre of the galaxy at about the same speed. This suggests that something outside the galaxy's disk is tugging at the stars, hence dark matter. Calculations show that a vast halo of dark matter surrounds the Milky Way. The halo may be 10 times as massive as the bright disk, so it exerts a strong gravitational pull. The inference of dark matter is based on absolute faith in the application of Newtonian dynamics. The need for dark matter appears in galaxies that are 100 million times larger than the solar system, and on acceleration scales 100 million times smaller than we experience on the surface of the Earth. The inference of dark matter could just as well be interpreted as an indication of the failure of Newtonian physics. People have, of course, considered modifications to Newton's gravitational theory as an alternative to dark matter. It's hard to do this without breaking something else fundamental. So hard that the widespread presumption is that it is impossible. Indeed, vast majority of modified gravity hypotheses quickly fail when confronted with the astronomical data, never mind the theoretical objections. For example, it is possible to exclude any modification that is simply based on changing the force law at a particular length scale. So what is dark matter? If asked what dark matter is, most scientists working in the field will respond honestly that they have no idea. WIMPs, weak interactive massive particles. This is one theory, an entire class of new fundamental particles that emerge from a thing called supersymmetry. Supersymmetry being a theoretical notion by which known elementary particles have a supersymmetric partner. This notion is not part of the highly successful standard model of particle physics, but might exist provided that Higgs boson exists, which we now know does. From the astronomical perspective, all that was required was that dark matter be non-baryonic and dynamically cold. Non-baryonic so that it does not participate in any of the Big Bang nucleosynthesis, or interact with photons, which is a good way of remaining invisible, and dynamically cold, which is slow-moving and not relativistic, so that it can clump and form gravitationally bound structures. Many things might satisfy these astronomical requirements. For example, supermassive black holes fit the bill, though they would somehow have to form in the first minute of creation? Well, there just may be a supermassive black hole at the centre of our galaxy, the Milky Way. So I hope that's whetted your appetite for further study in this fascinating field. Are dark matter and dark energy related? No one knows. The leading theory says that dark matter consists of a type of subatomic particle that has not yet been detected, although upcoming experiments with the world's most powerful particle accelerator at CERN may reveal its presence. Dark energy may have its own particle, although there is little evidence of one. Instead, dark matter and dark energy appear to be competing forces in our universe. The only things they seem to have in common is that both were forged in the Big Bang, and both remain complete mysteries. There is much to discover.
Something wonderful